All right, so in this presentation, we try to summarize the different types of like major, I guess, like studies that we do at the wall of wind. You can consider it also as like, studies related to wind engineering as a broader subject. So we're going to talk about the test design and planning using the wall of wind experimental facility. We have included the aeroelastic, aerodynamic, destructive, and wind-driven rain test protocols. And Amal will talk about the downburst simulation and some upgrades that we did recently in the facility. So we have basically two groups here, existing testing capabilities and recent and scheduled upgrades. I'm going to start with aerodynamic test, which is the most typical traditional wind tunnel study involving a model with pressure taps. Some examples that we included here. Wind effects on canopies attached to low and mid-rise buildings. This is actually like there were like different studies that we carried out over the past like 6 to 7 years, started from a low-rise building. It was a typical codification study where we included the focus. The objective was to examine the wind-induced loads on canopies attached to residential structures, low-rise residential structures, as the first step, and then we extended the study to mid-rise buildings. The advantage of the wall of wind is that we can incorporate we can use larger models. In a typical ABL wind tunnel, the scale is about 1 to 100, or in some cases, if we deal with larger structures, 1 to 200. In our case, wall of wind, we can go up to 1 to 10, 1 to 5, and that is a major advantage, especially for thin cell type of elements like the canopy, where the thickness of the canopy is critical. And the fact that in a smaller model, if you have to reduce the size, the thickness by 100 or 200 times, it makes it impossible, to include like several hundreds of pressure taps in there. You can see both models at the bottom. We had pressure taps both on the top and the bottom surface of the canopy, so we could get a net effect, which was critical, in the codification process. Another example is the wind loads on balcony rails. We examined another objective as a side product of this study was the effect of scale. We started with a very small model of 1 to 180, and then we moved up to 167, 1 to 25, and you can see here the difference basically between the different models. Again, going back to my previous comment, there's a lot more you can do when you increase the size of the model, and we can study in detail, the different smaller elements, building components and cladding. And at the same time, we can consider the Reynolds number effects, where we have like a larger model, and that corresponds to higher Reynolds number. One of the ongoing, actually more recent projects, Dr. Elawari is leading this effort. Wind effects on elevated homes that followed like one of the field studies that we did following like Hurricane Irma. We noticed we drove down to the floor decks, and we saw that there was significant damage on the underside of the elevated homes. There was not much literature that did wind tunnel testing on this type of structure. So we have the model that you can see on the right of the slide, including pressure taps and load cells on the base, the piles of the elevated home. By doing that, we get two kinds of data. So we have the pressure scheme on the surface of the building, but at the same time, we have the overall load on the foundation level. And the last slide that I have included in this group, the aerodynamic testing, is to describe the codification process. This is an important aspect of what we do, and it was raised also by the review panel during the renewal. The NSF is trying to promote this kind of activity. We want to enhance the building codes. We want to improve the building codes and wind standards. And this is the typical, I would say, like overview or the different steps that we follow in order to end up codifying the findings from a specific test. And we have several hundreds of pressure types, as I explained. We do some sort of area averaging, and you end up creating this ASC7 type of like polylines, the envelope lines, as we call them. And at the end, you end up, we can come up with design recommendations that we can submit to AC7 committees. And this is a successful example with the wind loads on canopies, ended up being adopted by ASC 716. And we followed up with one more proposal for the 722 cycle for the mid-rise buildings. All right, the second group is related to wind-driven rain test. Another unique capability of the wall of wind is that we can introduce rain into the flow. The process is similar to what we do with the plain wind. We have to make sure that the science is right. We have simulated the rain flow properly, and in order to do that, we have to compare it to the field data. So basically, we select the right nozzles to simulate the target wind-driven rain parameters. You can see some examples on the right here on these figures. For example, at the bottom one, the target is the gamma model coming from previous literature. And by kind of like changing the type of nozzles, the distance between the nozzles, we can try to match the target profile, the field profile. Some examples, the wind-driven rain on full-scale models. So this is a one-to-one scale, basically a real small structure in front of the wall of wind. We can do the same thing in smaller models or large-scale models. You can see at the bottom left, plexiglass model with rain gauges, where we collect we try to quantify the amount of rain that goes into specific areas of the structure. And on the right figure, you can see a close-up of the water injection system and the spraying nozzles. This is the outcome of the study. We can come up with contour plots that they show basically this particular example is the surface runoff rainwater. Wind is approaching, just to give you an example, a perspective here, wind is approaching from the bottom left corner. Let me add my pointer here. So basically wind is coming from this side. And what happens is we have flow separation and then reattachment on the opposite corner, which means that there is a lot of accumulation, rain accumulation on the opposite corner. And this is a very interesting finding, obviously, not something we didn't expect, but nevertheless, if you combine that with expected damage, we can see the effect of rain intrusion into the interior of the building. This is a different study that we did a couple of years ago. So this was the focus here was to see how the rain is distributed on the interior of the building. So we create artificial, openings. We can assume that we have a broken window or some sort of like breach on the roof or the wall. And we were trying to identify the distribution of rain on the interior compartment of a low-rise building. And by doing that, we wanted to enhance the public loss models. We can correlate the damage to the expected rain event. We use, some sort of absorbent pads in order to do that. And then we had the thermographic pictures where they show, the distribution on the interior surface of the house. Again, the same study here. We have an explored view of basically of one case where we have two openings. One opening is here and the second opening is here, and you can see the distribution based on thermal imaging. This is a full-scale study. It requires more basically preparation to do something like that. Obviously, when we deal with a full-scale structure, things take a lot more time. But the concept here was to compare the water intrusion collected in the basin behind the window for normal wind direction, about 60 miles per hour, between a non-impact window and an accordion shutter. So we see here the first case over here. This is the case of the non-impact window, where we have significant rain water intrusion through the non-impact window. And the second case is the case with the accordion shutters. This is something that we use here in South Florida to protect the homes, our homes, from the hurricanes. And you see that the rain intrusion is much, much less. And this was an interesting finding, basically comparison between even an impact window and the shutter, how they behave when the rain component is considered. The third group is destructive testing. And this is I guess the most, I should not say the most interesting, but it's the type of testing that you can see the effect of extreme winds on the structures that we test at the wall of wind. Obviously here, destructive testing, we deal with full scale, one-to-one. One example, this is a project funded by the Florida Department of Transportation. We wanted to examine the performance of span wire systems, traffic signals. The focus was basically this component over here, which is what we call the hanger system. Obviously, this started by observations after following like real hurricanes, where we had like issues for this type of traffic system. And what we did at the wall of wind, we came up with an approach. The first phase was to build a test rig that we can mount on top of the turntable in order to be able to rotate the test frame and examine different wind directions. The disadvantage of doing this was that we had a much smaller span length compared to what happens in reality, which is usually the typical span is 80 feet to maybe like over 100 feet. And here this test frame was at 20 feet. So we came up with an approach where we basically attach the ends of the wires to springs in order to simulate a larger span. And obviously we wanted to verify this approach. So the study was followed by a full span. This was approximately 75 feet from one wall of the wall of wind to the opposite end. The disadvantage is that we cannot really rotate this system, this test frame, and we tested only the 0 degrees and 180 degrees. But it was important to do that to validate the previous approach. The comparison was very good, especially for like lower wind speeds. When we exceed a certain wind speed, we discover the aerodynamic instability. I have a video, or maybe you've seen the video before. Arindam included in his presentation, but I have it here as well. After a certain wind speed, we go into the aerodynamic instability, and we've noticed like the instability in both forms, one-dimensional and three-dimensional, so galloping and flutter. And that was a very, very important finding, mostly because when we showed that to Florida Department of Transportation, this is exactly what they've seen, in the field. And it was very important that we managed to replicate that in a controlled environment, in a wind tunnel laboratory. Let me see if I can quickly play this video. So yeah, you see that like above the 110 miles per hour, you start seeing like the intense galloping of the system that leads basically to the failure of the top wire. This is a roof study about roof pavers, again, destructive testing. What is happening here? We have cornering winds. You have the cornering vortices generated, and this is basically, let me add my, then you have basically the path of the cornering vortices. This is the high suction zone, and as we increase the wind speed, you see that those pavers, they feel like this very high peak suction. And we have followed up with a lot more studies on roof pavers, basically, where you can, this is also like, on top of the research aspect of this topic, we have also like, this is a very useful tool for research and development to come up with like better solution on how to secure this type of roofing element. Amal, I'm not sure if we have time for the IMAX video. I'm going to pass it to you, and if at the end we have time, I can come back to this one and watch the video.
Okay, sounds great. So I just requested remote control, if you please.
Yes, and I approve that. Yeah. Perfect.
So the fourth type of testing that we do is the aeroelastic test. It's more complicated because we need to replicate the dynamic properties or the motion of the structure under wind excitation. The thing that certain structures will experience, you know, significant, I'm not sure what happened. I think it's slow from my end.
I can switch the slides for you. I can move the
Okay,
slides.
yes, please. So if you please can play the videos here on the slide. So as you can see from these videos, some significant vibration will change the aerodynamic forces on the structure. So we have to consider this for something like a bridge. On the left-hand side here, we see a sectional model of the bridge. We can control the motion by like side actuators. Also the same thing here, sectional model for this deck of the bridge. You can see from the flow visualization here, the wind-induced vortices created by this motion of the bridge section, which means that overall drag and lift forces will be impacted by the effect of this wind structure interaction, or the big vibration or deflections of the structure. So the structural behavior associated with the self-excited motion is what we call the aeroelastic behavior. Aeroelastic testing we consider as the most reliable approach because you consider both the shape of the structure, and which is basically the aerodynamic forces, but also you can predict the structural deformation and the aeroelastic feedback under this wind action, which means that the change in the wind loading based on the structural movement. Yeah, next please. The previous video actually showed that we were able to control the sectional model by side actuation system, but we also can do a full modeling of the entire dynamic properties of the structure in terms of stiffness, mass, moment of inertia, and other scaling items. So we have to follow like a long list of scaling ratios so that we can replicate the dynamic properties, mode shapes, and modal frequencies of certain of like the structure of interest. Next. The idea is that we need to replicate the essential mode shapes. So we have to first identify essential mode shapes, their contribution to the total dynamic response of the structure, identify the frequencies. Here you can see the prototype frequency and then what we have as a frequency scale, and then the target frequency based on that frequency scale. So we try to replicate that and we assess this based on free vibration test. Next. Next, please. Yeah. Here I'm just showing like what type of instrumentation we use for aeroelastic testing. We can have like load cell like this blue JR3 load cell here at the hinge of this transmission tower. We can also get some strain measurements using strain gauges and accelerations. And I must say here, for example, for this particular model, we simulated the dynamic properties using frame structure that you see on the left. However, this doesn't mimic the shape of the structure, so we needed to add non-structural elements, the cladding elements that you see here on the zoomed in photos on the right. So together, the two would mimic both the dynamic properties, frequencies, mode shapes of the structure, and also the shape, so we can replicate the wind forces on the structure. Next, please. We recently had a multi-span transmission line system tested at the Wall of Wind for this transmission line, self-supported transmission line. The structure was reduced or scaled down with a 1:50 length scale for the towers, and a distorted length scale for the cables using 1:150. Johannes, there is a video on the left. If you please can play that one. This shows the technology we use to initiate the excitation, so we can measure the free vibration of the structure. So we basically induced kind of displacement at the top, the top point of the tower, and then we let it freely vibrate, and then we measured the accelerations. Next, please. This is also a video showing the wind response of the entire system, where you can see also the cables connected between the towers. And the good thing about the Wall of Wind turntable, it's like 5 meters, so we can fit in like this kind of multi-span structures. Here on the right, you can see the wind speed, 30 miles per hour, which in full scale, because that was reduced the scale wind speed, in full scale, that was like hurricane winds. I guess it was like 100 or 130 miles per hour. Next, please. Okay, so what we can get out of an aeroelastic modeling and testing. Basically, first, system identification. So we can measure accelerations under like free vibration without wind, which what you see here on the left, the decay of the motion can give you the dampings of the structure. And then you can do the same for wind so that you can get the aerodynamic damping of the structure. Also, you can identify the frequencies of the model, like what you see here on the right-hand side. We can identify the frequency for each mode. So we excite the structure in a certain direction that mimic the first mode shape, for example, and then we see what is the corresponding frequency by plotting this PSD. Next, please. Also, with aeroelastic testing, we can also filter all the components in the response that we measure. So we can, first of all, we measure peak response that you see here in a black line. And then we can filter that to get the mean response. And then by filtering the resonance in, the dynamic response component into like background and resonance, we can see the contribution of the resonance into the total response of the building. Next. Yeah. Once we filter resonance, we can estimate dynamic amplification factors. We can also, and how the DAF, the dynamic amplification factor, change as we change the wind speed, which what you see here on the top left plot. On the top right plot, we can see the aerodynamic damping variation with the change in the wind speed as well. We also, as I mentioned, we measure strains, so we can get like strains, which we can convert later to drag forces or like bending moments on the frame that we are testing. Next. Okay, so for the new capabilities that we have currently, like ongoing improvements at the Wall of Wind or upgrades, Arenda mentioned about the automated roughness system, which will significantly reduce, of course, the time of the setup of the roughness. We can test open terrain, suburban terrain in fewer less time. We also currently got the traverse system, this robotic arm, which will help us to quickly characterize the wind field. So basically, we will mount the Cobra probes to measure wind speed, time histories on this arm, and then do the motion or the movement from point to point that much faster. Okay. This is not a video, it's just a photo here on the left shows the simulation of the non-synoptic downburst flow. We're currently building the full-scale downburst simulator at the Wall of Wind. We plan to test that next month, characterize the results and publish it in 2 or 3 months. This is non-synoptic wind, which means it's local in time and in space. So we think that this will be like larger scale simulation of downburst events that would allow larger scale testing of building and how this downburst flow would impact a different type of buildings and other infrastructure. We will talk about the hybrid simulation capabilities that we are developing in collaboration with Lehigh in few, I think, minutes after this presentation. Next. Also, we discussed in the morning about our new PIV system, partial image velocimetry system, which will enable and advance our fundamental knowledge of the flow or the wind structure interaction. We are almost ready to implement that in the facility. So we have the equipment, we know the vendor. We should be ready to operate the system. This is, I must say that this is an MRI award from NSF. The award number is here. And I guess that's it for this presentation.